Procedural terrain generation is a process by which we can generate beautiful worlds of our imagination at runtime. Why do we care? Well, because our favorite games like Minecraft create endless terrains that never repeats. Or Terraria, a 2D version of Minecraft in this regard, also can create these beautiful worlds that never repeats, that feel random and organic. How do they do this? One solution we can have is we're going to create a very big world, handcraft every height, store it somewhere, and then spawn players at random location. But one day, one adventurous player would explore everything and the game would get old. So the solution could be that we're going to have a set of these infinite worlds, choose one at random, spawn the player at a random location, and rest assured that nothing will repeat. Well, it will, right? Because the set is finite and the world is finite. Even if we wrap the world, essentially creating a spherical world, it will feel old. So how do you ensure that nothing repeats? The world doesn't repeat and the level doesn't repeat without having infinite memory and infinite time. One solution could be we're going to use analytic terrains like y equals sin x. Then we don't need to store every position because we know how to generate sin x at any given point. But that is boring and not realistic because it doesn't accommodate the randomness. So we have to somehow accommodate the randomness of nature in our code. Enter generation algorithms. We're going to explore 3 generation algorithms, each more complex and interesting than the previous one. Let's start with the more basic one, cellular automata. We're going to start with a grid of numbers, zeros and ones. 0 being passage and 1 being wall. You can name them anyhow you want. Cellular automata is an iterative algorithm that will transition the zeros and ones to something else with a very simple rule. The rule is, consider this red cell and its Moore neighborhood. In its Moore neighborhood, we can see 8 surrounding cells, and including the cell itself, we have 9 cells. If among the 9 cells, the majority of the cells are walls, in the next iteration, this will also become a wall. Otherwise, it will become a passage. So this is a very simple transition rule. We're going to apply the transition rule, iterate over the worlds, let the world evolve. Starting with this blocky and grid-like world, we're going to end up with a beautiful organic world out of nowhere. Let's see the demonstration. This is the output of cellular automata. Believe it or not, it started with a grid-like cell and ended with this organic structure. You can use this in your game as cave generation or terrain generation. This will feel natural. And it never repeats. I'm going to run this again, and this evolves into a different world. Run it again, evolves into yet another different world. Nothing repeats. Moving on, midpoint displacement algorithm, our second algorithm in the list. We're going to start again with something very basic. Start with a straight line segment, call it AB, find its midpoint C. Now, find the normal of AB. It can be upward or downward, it really doesn't matter. And along this normal, we're going to displace C. So let's find the displacement vector by multiplying by the displacement amount. The displacement amount is our controlled amount. It can range from negative h to positive h, and we're going to choose anything in between with a random function. Multiply the unit vector with this value to generate our displacement vector. Our displacement vector denotes where and how much we need to displace the point C. Let's displace it along S and call it C prime. Now connect A to C prime and B to C prime. Forget about the previous line segment AB. Repeat the algorithm for AC prime and BC prime, and we're going to get our terrain. Here one thing to note is the next h, the displacement max amount, will be reduced. So it will look more organic. And we can repeat it as much as we want to create more and more resolution. Now we have our terrain. How to make it endless? We can have 2 overlapping terrains, and when the player moves, move both the terrains together. When one of the terrain goes outside the screen, we can make the next terrain the front terrain and generate a new back terrain. And this way we can have an endless crawlable terrain. Let's see a demonstration.
As you can see, you have created three terrains with the same algorithm, the midpoint displacement algorithm. Their differences are that they differ in level of details. As you can see, the front one has more details in the back, and then the last one is very less detailed, and also the movement speed. The movement speed difference creates a parallax effect. The more front the terrain is, the faster it moves. That's what creates the parallax effect, as seen in video games. And the level of details is dictated by the maximum height, how the maximum varies from iteration to iteration. The geometric vary is changed and thus creates the level of details for each terrain. Okay. So now comes the more interesting terrain, a 3D terrain generated with Perlin noise. Any noise would do, but we have implemented ours with Perlin noise. So the idea is you start a tessellation, begin a tessellation in the XY plane, and you can store the tessellation as a list of lattice points in the purple points in this diagram. And then what you do is you calculate a height value for each point. How do you calculate? Well, there comes our noise function. The noise function takes these points coordinates as input and will spit out a value from -1 to 1. You can multiply with the maximum height to get a height value for each coordinate. And the noise function does not use directly the coordinate. You might want to reduce or scale down the coordinate values x and y in order to make a smoother terrain. Okay. Here we have this Perlin noise. You could have used other noises as well. Then you take each lattice point and extrude it upward or downward depending on the height map, the amount that was dictated by the noise function, and then you get different heights for each points, and that creates a terrain structure. So how do you make it endless? So one way could be to make 2 worlds or 3 worlds ahead of time, and as the player moves on from one to the other seamlessly, you destroy the previous world and bring in a different world ahead of time, and thus you always have a 2 or 3 worlds ready, and as the player moves, you swap out the worlds or maybe remove world, grow and shrink. Another very naive approach could be these layers, the top layers or the front layers height values could be propagated backward to the later layers. This propagation would make it seem like you are flying forward. So if you are flying forward, propagate the height map backward. Where change the height map in the reverse direction of your movement. That would also create an illusion that you are moving or flying through the terrains. Another change we could bring here is use different noise values, Worley or simplex noise. So let's see a demonstration. So here we have used Perlin noise to generate this terrain structure. There is nothing else going on. All are dictated with height maps that are dictated with Perlin noise, and if we run different times, it is going to output different terrains, and the new generations are also random. They are not hard coded or anything. They are random, and this artifact, that new world is growing, it could be solved by having a bigger world, and the generation would be seen in a smaller portion of the screen, and thus reduce this effect or artifact. Okay, but how did we make it seem realistic? If you took this tessellation and extruded it upward or downward, it would give you a very ugly wireframe terrain. How do we go from this to this beautifully rendered terrain? Well, there are many approaches. We took a very simple approach, that is, we chose the color based on the height. If the height is greater than a particular threshold, we mark it as a mountain. If it is less or equal to that, we mark it as the ground. And then we also add a water plane going on. But that would also not output exactly this. Well, the deeper the terrain is, the darker it seems. So this mountain region is dictated by this threshold value, all right, but the upper mountain values, the upper mountain region is lighter than the lower mountain region. That creates also a nice effect. And you could also, we have used 2 levels like mountain or ground, but you could also make it more levels, and a simple color would be enough to create this nice effects then. Or you could go with texture and make it even beautiful. There are some references for you to explore. Thank you.